Lecture number 12. It's the last lecture in the short course. So, okay. So today we are going to talk about applications of ML in numerical weather prediction based on the work we have been carrying out in our group at IIT Madras. So basically, this is basically looking at the sensitivity studies and calibration of mesoscale weather models to improve forecasts of both monsoons and tropical cyclones. This was a work we carried out as a part of the National Monsoon Mission phase 2. Okay, so I was one of the PAs of one of the projects. So we got generous funding from the Ministry of Earth Sciences. Apart from the generous funding, we also had unlimited access to the Aditya server, the supercomputer in IITM. So we were able to do a lot of runs. So once you have so much of data, it's possible to use machine learning, and then we try to use our machine learning background to see how we can approach this problem. So two PhD students have come out of this. One is Sandeep Chinta, who is right now in MIT as a postdoc, and now Baki Harish, who is just finishing. He just submitted, so he's also going as a postdoc to Netherlands, where they want to extend this work and calibrate models for wind energy, solar energy, and so on in the European Union. All right. So basically, this is the let's look at the right side of the view graph. So basically, what is numerical weather prediction? Okay, let's go to the left side first. It is an initial value problem which uses the present. The idea is to use the present state of the atmosphere to forecast in time as well as in space. Okay, so the forecast, it's basically a forecasting problem. So consider X superscript nu as a new atmospheric state and F as the prognostic model which governs the atmospheric state, a dynamics model, let's say. Then the atmospheric state at an incremental step is given by the new state is the old state plus F operating on X of old into delta of time. This is written as an explicit formulation and so on. So the idea is, I hope the idea is clear to you. Now we have got both observations as well as theory. Based on the observations and all that, and then you get what is called, and also from global general circulation models which are at a lower resolution, you get boundary conditions, right? You get boundary conditions which have to be constantly fed. So the boundary conditions have to be constantly fed even if you are downscaling and approaching the problem in a, so suppose you want to go down to a model like WRF, where you're looking at finer scales like 12 kilometers, 5 kilometer, 3 kilometer, what have you stuff. So these GCMs basically will give you at 100 by 100 or 50 by 50 or whatever. So there'll be some forcing always from the boundaries, which is coming from a general circulation model. So we start out with an error. There is also initial error when you start with the initial condition. There's initial error, there's a boundary error, and so on. So therefore, we start with error, and so we live with this error. So thousands of investigators all over the world have tried to work on this elusive problem of how to get the best weather prediction, so on various types of systems, squalls, storms, tropical cyclones, monsoons, and in the ISM, the Indian monsoon is very enigmatic and it's very difficult to capture. So because it's quirky nature, and it's difficult to understand fully what is going on, though we have a reasonable grasp on the physics, the mathematics, and so on. Largely because I'll tell you there's something called parameterization in the model, which is akin to this concept of a black box in neural network and so on, right? So because we are not able to resolve the fine scales, we just call it as a parameter and proceed. For example, in heat transfer, we'll say whatever we don't know, we'll say the heat flux is directly proportional to temperature difference, the heat flux is directly proportional to area, and the proportionality is replaced by equality. It is like God, H, heat transfer coefficient. 100 years you're talking about the same heat transfer coefficient. However, we will correlate heat transfer coefficient as a function of various geometries, turbulent flow, laminar flow, whatever. We'll classify the flows as internal flow, external flow, and so on. Okay, so this parameterization is a problem. Okay, so people like Prandtl try to address that from the boundary layer theory and so on. So anyway, so I'm deviating from the subject. Let's get back to this. So that's on the right side of the rightmost side of the view graph. Then theory, you have the governing equations which govern the behavior of the atmosphere. So then based on this, you do what is called model development. Okay, so which means you make the equation solvable by computer, you code, you use whatever method you want, spectral method or finite difference, finite volume, whatever. Then the model simulation, you're able to predict in both time and space, and you get the model output. Okay, typically you will get the velocities, water vapor mixing ratio, and long wave radiation, short wave radiation, whatever you want, right? So the governing equations basically are 7, okay, which we have considered. The 3 momentum equations U, V, W, the 3 velocity components. the conservation of energy, which is basically governs the scalar temperature. Please note UV, W are vectors. So the conservation of mass equation for the air density, then the conservation of water vapor equation for water vapor mixing ratio, it's Q, and the ideal gas equation because it's a compressible framework. All right. So these are the 7 equations which have to be solved. It's all easier said than done because you're you're going to solve it to the whole of Indian subcontinent, or in a GCM you'll solve it on the whole planet. Okay. So the governing equations are discretized to make them solvable on a computer. For example, the discretization of the 1D conservation of water vapor equation, basically the partial of Q to the partial of D equal to minus U of the partial of Q to partial of X. For example, one way of formulating would be Q of XY at time step T plus 1. Right hand side is all at the time step of T. The left hand side is a time step T plus 1, which means whatever is there on the right hand side should be known to you. Please note on the right hand side, the velocity is also there. So the velocity itself is one of the unknowns. So to cut a long story short, it is very clear that the equations are non-linear because the right side contains terms which are also part of the equations which you want to solve. All right. So this leads to what you have to do: upwinding, first order upwinding, second order upwinding. Many schemes have been developed. So the flow could be recirculating, what sort of upwinding scheme you have to use, and so on. All right. The grid also plays a critical role in the model accuracy. However, many processes occur within a single grid, which might be impossible to resolve. That's where the problem starts. Okay. So Reynolds averaging is basically a widely accepted method used to account for the effects of subgrid scale processes. So after applying the Reynolds averaging, that means you take care of the fluctuations and put an over bar. That means you're integrating over the time. Then, for example, the 3D water vapor mixing ratio equation would look like this. So the partial of Q bar by T minus is equal to so many terms are there. Okay, so you've got fluctuating terms as well as over bar of fluctuating terms, over bar of mean quantities. The mean of the mean is the mean, right? So U bar, Q bar, bar is UQ bar, whatever. So in the above equation, the vertical diffusion can be correlated. For example, look at the last but one term on the right hand side. So it has got a cross component. There is a fluctuating Q dash, there is a fluctuating W dash, and then this is W dash, Q dash over bar. That means that's the average. So what it is to then immediately hands up, surrender. We can't do that. I mean, so you just cannot, unless you do for a DNS, direct numerical simulation, it is not possible to capture. The moment you get a term like this, we start sweating. So what do? We say that this is equal, this is a royal approximation. We say that is equal to K into the gradient of the average quantity. So this is the beginning of all troubles. This also appears to be the beginning of the end of the trouble for your ability to make the equations tractable or handleable. But this is the beginning of all troubles in a field like atmospheric science, because this parameterization may not be adequate always. Okay. So what is that K? Okay. Now the question is, K is some parameter. K can be whatever. Okay. Depending on whatever whichever quantity you are looking at. So therefore, is the value of K always the same? Is it not grid dependent? Can you use the K for the same some event happening in Korea, China? I mean, there are many parameterization. So this helps us to break the deadlock or the log jam. Otherwise, we will not be able to proceed further in our quest to forecast by solving the equations. Okay, instead of just using a Fourier series, time series, and then using a brute force time series analysis or a neural network. All right. So right side, this is a familiar picture. So this is taken from the COMET program. So many processes are taking place in the atmosphere. Multiple physical processes occur at subgrid length scales. Okay, typical numerical weather prediction NWP model will have hundreds of model parameters, and to consider the effects of all these subgrid scale processes. Now, what we do is, in a program, basically default values of the model parameters are available. Often you don't know, you just run the default mode. So often people don't even recognize what is the default parameter and who are the investigators who put this into the model, because everybody puts his own. So you can see so many. So the models are named after their investigators. Okay. So crayfish model, this thing, right? So you have so many models. So these have been obtained based on theoretical and or experimental investigations conducted by those modelers who are collectively called as scheme developers. So the scheme developers, they've basically taken, just like we have taken an ensemble of events, they have taken a specific event or a series of events, And then based on that, they say that they would have figured out, they would have written a paper that if you put this value of parameter, it is very good. But can it be used on all occasions? And this thing, is it that it is like God, which cannot be touched, holy cow or something? That is open to question. Okay. Now, what are the objectives of the present study? I mean, this is the last 6 years of work, 6 or 7 years of work, 2 PhD students. Look at the bottom center, using the weather research and forecasting, which is a free to use community software, WRF, developed by NCAR. Carry out simulations for the Indian tropical cyclones and heavy rainfalls events in the monsoon period. Okay, so I'm going to talk only about the cyclones. If you want to have a more detailed version of this lecture, so I'm going to give a talk on the 22nd. So I'll give a full-fledged talk on this whole thing, the expanded version of today's lecture, and this will be physical offline at the computation data in CDS auditorium, 11 o'clock next Friday. Okay, so you're welcome to join that. Okay, left side, identify the most influential parameters using machine learning based sensitivity analysis methods, and then you identify the sensitive parameters, look at the parameters and see whether you can calibrate. So the right side is calibrate the influential parameters obtained using machine learning based multi-objective optimization. So these terms may look scary, but we will remove the scare by the end of this lecture. All right. So this much of today's lecture is available in a recent paper, which is based on the PhD work of Harish Baki. This is come in the EDU journal. Geoscientific model development is open access. You're free to download. The paper got accepted it's very fresh. It just got accepted 3-4 weeks back. All right. Okay. They have a new way of this thing where you just post it on the archive, then there'll be some reviewers who ask questions. There are also anybody can ask questions, and the authors are supposed to answer everybody's all these queries, and you have to seriously answer the queries of the reviewers, and then finally it gets accepted. This is a new model, all right. Okay, now list of tunable parameters. So there are like 24 parameters in various schemes. What are these various schemes? So we have chosen the surface layer, cumulus, microphysics, short wave, long wave, land surface, and planetary boundary layer. In each of these, there are various schemes. Now, first you have to do what is called a scheme sensitivity study based on your events, past events. So you do a hindcast. You just do which of these schemes influence, which of these schemes do. So these are all radio buttons. For cumulus, you will have a set of schemes. Microphysics, you have a set of schemes. So all this we have done last 10 years. We've done it for various events. Okay, and there are several ways of doing this. You could probably compare your predictions with the rainfall, IM degraded data, you can, or iMerge data, or you can look at TRMM data, or you can benchmark with respect to radar reflectivities. So whenever you're benchmarking, there is something which you take it as more reliable than yours, or which you look up to. That is the so-called truth. Truth is an elusive thing. Truth, we don't know where the truth lies. But so even this is truth to a certain extent. So as they say in spirituality, you go from lower truth to higher truth. Okay. So from a lower truth of a model, you go to a higher truth. The higher truth could be any of these things. Okay. So based on that, we have identified some schemes. I am not going to the schemes now. So let's say the P1, P2, P3, P4 are the surface layer. So if you look at the default, it's 2e to the power -5. But there is a considerable look at the range, it's 1.2 to 5. P2. So that is a parameter for heat moisture exchange. Then the next coefficient, the model developer said 0.0185, but that is in the middle of the bang, in the middle of the range. Then the P3 is the scaling related to surface reference. Let's look at the physics right side. Just forget the left side. Just let's read out the last column. 1 von Karman constant, multiply for downdraft mass flux rate, multiply for entrainment mass flux rate, starting height of downdraft above USL, average consumption time of the cape, okay, which will be very important in thunderstorms and all. Maximum turbulent kinetic energy, scaling factor, intercept parameter. All these things have a range, and we don't even know that the WRF runs with this default parameter. So what we did was, we want to needle it, and we go to we get down to the bottom of this, and we'll start needling it and see whether changing that parameter is first affecting the results. Okay, and then we should not do it for 1 or 2 years. We do for an ensemble of events. We do it thoroughly, and then for Indian conditions. So this is what we have done. Okay, so you can see all this. So there are some 24 parameters. Okay, Now you can see for these 24 parameters, we want to find out the sensitivity and then rank them. So it is a humongous task. It is here that machine learning comes to your help. It's okay. This has to be taken with a pinch of salt. You can't do a machine learning unless you have a data set. And you can't have a data set unless you have a numerical solution. Therefore, you will have to generate some numerical solutions and go for a replacement or alternative, what we call it as surrogate. So we call it as a surrogate model. Huh? So this surrogate model, we have used machine learning techniques to do this surrogate model. Okay, let's proceed further. So the events which you have considered are basically cyclonic storm, severe cyclonic storm, very severe cyclonic storm, Thane, Philin, Leher, Muddy, Helen, Mora, Neelam, Vieru, Coman, and Roano. All the tracks of all this, these are basically 2011 to 2016. So you can see the tracks of all this, these IMD tracks of all these past cyclones. All right. So the Wrf model configuration, basically, it's the two domain nested domain. So the outer is 36 kilometers, the inner, that's D01 domain, the D02 is 12 kilometers. Okay. So this is called two nested domain. Okay. Now the initial and lateral boundary conditions are basic. FNL is final analysis. FNL final. The final analysis, which is available free for you to download. Input data interval 6 hours. Model integration is 84 hours. Then the resolutions I've told you. Then the number of grid points 240 by 240, and this horizontal and the vertical levels of 49 for the D1 and 361 by 361 for the D2. Integrations time step is 60 seconds for D1 and 20 seconds for D2. The overview of the physics schemes. How did we choose this? This is written in a separate paper. So this is the first thing which you have to do. If you have to work with the NWP models and you want to do some calibration or sensitivity study, first thing is sensitivity study of physics schemes. Long wave, we have done RRTM. Short wave, the Dudia scheme. Surface layer, the MM5 similarity scheme. Land surface physics, unified Nova land surface scheme. PBL, Yonsei University scheme, and Cumulus is Kane Frisch, which seems to be working well for Indian conditions, and 6-class scheme, the W single moment 6-class or microphysics. All these things we have explained in our paper and why these are important. All that in earlier papers. You can, the interest of time, I'll skip this. Okay. Now the first part is which of these parameters influence your output results maximum. That is the first thing which has to be done in a scientific fashion first. Then once you find out these are the parameters, what are the best values of the parameters? So that is the objective of today's lecture. First is to quantify the sensitivity or the parameter sensitivity. Parameter sensitivity is the quantification of the influence of a parameter on the model output. While several methods are available, two broadly used global sensitivity methods are multivariate adaptive regression spline, which is called the MARS, which is a regression based method. Then there is a variance based method called the Sobol method. The Sobol is basically a Russian and Jewish mathematician, okay, who first, in a series of papers, he showed how the variance can be used. Okay, we'll talk about all these a little later. All the parameters are normalized from 0 to 1, and a total of 250 random parameters are obtained for the 250 random samples are obtained for the 24 parameters. That is P1 to P24 one set, P1 to P24 second set, P1 to P24 third set, like this P1 to P24 for 250 sets. Now we have to generate randomly these samples so that one sample cannot be linked to the other sample. The covariance of the samples must be 0. So very good statistical techniques are available for this. The quasi Monte Carlo goes well with Sobol. You can also use what is called LHS. Okay, there are new techniques, that is Latin hypercube sampling. Huh? Okay, and quasi Monte Carlo scheme is available in Python, right? Baki, it is default.
Yes, sir. It is there in Python libraries.
It is there in Python. You don't have to code. You have to just take it. Okay, just like go and order coffee in a coffee shop. You can just take it. All right. So these parameter values 250 by 24 will be used as input to the machine learning algorithm. Okay. 1 second. maybe the laptop is getting drained. So I'll just put it on charge. All right. Okay. Okay. So these parameters will be used as inputs to the ML algorithms later. So I've given difficult to read two sample sets, 0.08. This is just, you can see all the numbers vary between 0 and 1. Now, 250 samples are taken for each cyclone. So for 10 tropical cyclones, 2,500 simulations are required. So 2,500 simulations for 84 hours in the Wrf and all that, where you're solving your nonlinear partial differential equation, 7 of them. So that is the first challenge. Okay. Okay. From the Wrf model simulations, many output variables are there. We chose these: 10-meter wind speed, surface air pressure, surface air temperature, precipitation, PBL, planetary boundary layer height, outgoing long wave radiation, downward short wave radiation flux, and downward long wave radiation flux. Now, you calculate the root mean square error between these model simulated variables and that of the observations, estimate them, and average out over all the cyclones. Therefore, the output will be just 8 RMSEs. Okay. I come again, the output will be just 8 errors. 8 errors in the first one will be the error in the wind speed. The second will be error in the surface air pressure. Like that, it will be 8. Okay? There are 8 such things. This 250 by 8 matrix will be used. This 250 by 8 will be used as a target in the ML algorithms later. So you've got a 250 by 24 as the input, a 250 by 8 as the output. Okay. Multivariate adaptive regression splines method, as the method suggests, it is based on regression. What you do is, you just first brute force. You just use brute force and say that all the 24 variables are affecting your solution. Okay. Proceed like that. Okay. Now, this is called the forward procedure. It builds an overfitted machine learning based regression model considering all the variables. Now you look at the R square error, whatever metric you want, and then you say out of these 24 variables, you remove one variable, 20, it becomes 23 variables. Find out how the R square improves, then remove one more variable. So like that, it systematically keeps on removing. So first it takes all and chops off one by one. So this is the forward and backward procedure, and it proves the overfitted model by discarding one variable at a time. And then finally, it will come to the minimum number of variables, which will help you have a good R square. Okay. After the training, this model can successfully correlate the inputs to its RMSE values, which means after you do this, the whole idea, it's like it's a regression. If you give the 24 values, it will give you what will be the RMSE. Okay. So that is the beauty of this. The importance of each variable is the increase in the generalized cross validation between the pruned model. So the generalized cross validation is the metric. Okay. So it is easily definable mathematically. I'm not going to that now. Between the pruned model and the overfitted model. Okay. So the machine used is Aditya server in IIT Pune. Maximum is 8. It's almost nearly a 1 petaflop machine. One node is 16 cores, 64 GB RAM, not RAM. It should be RAM. Okay. 360 cores and multiple nodes used for our calculations. So we did 2,500 simulations, required 92,160 hours of CPU, which means real time of 3 months. So you have to just wait for 3 months not to complete the work, just to complete the simulations, right? So it is high performance computing. It is big data. Okay. So all those things which come under big data, machine learning, all that, this problem satisfies. Okay. All right. Now, so this is called a heat map. So I don't know how some of you may be aware. So we just plot the sensitivity by using a heat map. So you can see that the dark green color, as given by the legend on the right side, dark green color means it's highly sensitive. So you can see that the P3 influences WS10 very highly. The P6 influences the rain very highly. The P10 influences the outgoing long radiation. This way you can see that. The next will be, you will see that P14. So P14 influences what all? It influences SAP very highly. It influences SAT, okay. Then it doesn't influence, for example, OLR and other things. So this will give you this gives a very good snapshot of the influencing parameters and the output variables which they influence. The Sobol method is basically analysis of variance, Anova, which many of you know from simple statistics courses. The total variance of a model output is basically considered as equal to the contribution of individual parameter interactions. Okay. However, the estimation of variations from all the contributions requires an order of 10,000 simulations, which is impossible to perform through the Wrf model. Therefore, what we do is, in order to accomplish the Sobol method, we go for a machine learning. So the machine learning algorithms are used as surrogate models to mimic the outcome of the Wrf model. So what you do is, you do a limited simulation, the full-fledged forward model physics simulations of the Wrf, and then you basically develop a machine learning algorithm based on each of these, either of these: Gaussian process regression, support vector machine, random forest, regression tree, and k nearest neighborhood. Okay, so the Gaussian process treats the whole process of multivariate Gaussian model. Okay, where we look at each of these. In that multivariate, each of these Gaussian has got a mu and a sigma. Okay, and these are indeed the learning parameters, and it tries to fit. So a very crude approximation is given here, where something is a sine wave. You can take an ensemble of 7 or 8, which is the prior sample which is generated. The data is given in green, and after that you have got a nice model. Okay, so this Gaussian process regression is basically multivariate, and the nearest equivalent is possibly, for example, the Kriging. Okay, the Kriging which they use, right? Which the Kriging in use in many fields, which some people don't believe in. So the Gaussian process regression is based on that. Okay. Now, the support vector regression or support vector machine is basically divides the data into several hyperplanes. For example, right side, if you put a green hyperplane, it will classify data into the top line or the bottom line. Like that, in an n-dimensional space, you can put many such lines and so on. And so it's excellent for classification. All right. So, okay. Now come to random forest. So the random forest is basically a decision tree model. It builds a decision tree by selecting a random number of features. Okay. So suppose in a random forest, you collect a lot of fruits. Okay. Fruits, how are they? Fruits are classified into banana, apple, and orange based on color. Okay. Based on shape. Okay. Based on size, whatever. Then there are various classifications. Then your new fruit is coming. The new fruit is put into the first model. First decision tree says it is banana. The second one says it is orange. The third one says banana. So suppose you have got many decision trees. 8 out of the 10 decision trees say it is banana. Then majority win. So it should be a banana. So this is like, so this is a very simple example I told you. This is very much used in fintech, financial technology and all that, where they look at credit worthiness of an individual, of a company, and so on. Okay. So this is basically a random forest. Now the regression tree is basically, okay, regression tree is basically, I want to buy a mobile. Okay, then I want to have a decision tree. If it is less than 6 GB RAM, I will not buy. If it is greater than 6 GB RAM, I will buy. If it is more than 1 lakh, I will not buy. If it is less than 1 lakh, I will buy. I want a front camera, rear camera. If it doesn't have 3 cameras, so like that, there is a decision tree. Yes, no, yes, no, yes, no, yes, no. So you'll do this. Okay. So for regression problems, so regression tree is basically a decision tree method in which the data side is, so all this, it is divided into what is called leaves based on least sum of residual at a decision node. For regression problems, the final prediction will be the mean of the partition created at the end of a branch. Okay. So coming to k nearest neighborhood, we already discussed this. Suppose there are two classes, orange class and sky blue, rammer blue or whatever. Then there is ink blue point is coming. The ink blue point cannot be, because ink is not a classification. It has to go into category A or B. Then we look at the centroid of each of these clusters and find the distance of this point to the centroid. Whichever is nearest, we'll assign this to that. That is a k nearest neighborhood. So this also we have done. Okay. So all these are taken from internet. Please note that in future in presentation, even if you take a single picture, suppose this picture is on the YouTube or something, they'll say that IIT professor is copying and all that. So better to be on the safe side. Whenever in doubt, cite. Okay, CIT. So these are all these pictures are taken from these sources. All right. Okay. Now Sobol method. Now if you see right side, it's a very busy set of pictures. Okay, I'll tell you what these are. Though we have taken the average of the RMSE for each of the cyclones, of all the 10 cyclones, suppose you look at the spread, what will be the RMSE for cyclone 1, 2, 3, 4, 5 in each of the 5 methods, like the random forest, regression tree, and all that. And then look at the spread as well as what is the R squared for your design output quantities of the 8. What are these 8? Wind speed, 10 meters, then SAP, this thing, planetary boundary layer height and all that, rainfall and all that. Okay, if you look at all this, you can see that the Gaussian process regression scores very highly on two counts. First, the R squared is consistently high across all your variables of interest. Second, the spread is very less. Okay, so therefore, the Gaussian process regression is the best way to deal with this. So, of all, please note that today we have learned this. So, we have used this 5 machine learning algorithms, but the neural network is not used. Don't think that machine learning is equal to neural network. Neural network is just one of the techniques. And also, these can be at least little bit explainable. So this is basically at least partially. So this is explainable ML. But suppose we do deep learning, huh? So it will keep on, all this will go like this, huh? Then you will get this W1, W1 to W2, 3, W2, all these weights. After that, it becomes a black box, right? So we don't know what the neural network is doing. That is why some people will think that what is that mumbo jumbo it is doing. So I try to demystify it by giving some hand calculation. But once you go to do neural network, you can't study it. I mean, what is the physical interpretation of each of these weights and all that? It's very difficult. But if you want to extract some physics, what you can do is you can change the output, you can change the input and study the output. And by playing with the neural network, you can try to understand what is going on in its mind. Okay, but as such, it is overwhelming, the number of weights and all that. What are these intermediate variables? They are all unphysical quantities and so on. Therefore, that some people still are uncomfortable with with the neural network, though a lot of advancements have taken place. Okay, now to cut a long story short, from this slide, it is clear that the Gaussian process regression is working very well. Okay, so based on this Gaussian process regression, pseudo samples are generated, and then using the samples, the Sobol indices are evaluated. Now you can see again the heat map is put. Now please note that we have arrived at this heat map from 2 routes, so that the confidence level is increased. Now let us see together. The top one is based on a regression. The second one is based on variance. Okay, so the normalized scores are given like this. So now we are ranking the parameters. The highest influencer is 14, followed by 6, 17, 22. Now we'll see whether the other model, okay, the Sobol model, it also seems to give the same. Therefore, you can take a cross section of these and say from two different methods based on this simulated data, and then going through the machine learning, all the Jamela. Finally, we are able to find out what are the influencing parameters. All right. Okay. Now, if you write down the influencing parameters, the 24 has now become 8. Correct? P3, P4, P6, P10, P4, P15, P17, P22. Obviously, when you say these are the influencing parameters, if you write a major journal article, the reviewer is going to ask you, out of 24, why do you think these are important? Because what is the science? Okay. So after all, you are saying you are all supposed to be scientists, so you tell us. So we have written a lot of description about why the von Karman constant, the roughness constant, then the scattering tuning parameter, diffusivity angle, multiplier for the saturated soil, and the profile shape for the momentum diffusivity are important. So we've written that in the paper. You can take a look at this. So finally, now we have said that these parameters. So we have to work with these parameters and tune the model such that the P3, P4 up to P22, we change the default values which is there in the WRF to some other value which is acceptable, which is based on an error minimization, based on again simulation. So this activity is called calibration of the numerical model. So you can see each of these as a range, and there is a default which is either in one end or in the center. Therefore, there is ample scope for us to improve. And we have now solved 50% of the problem. We identified which are the most sensitive parameters. Right. Now, the second paper, which is the parameter calibration, is just now got accepted last week. Correct, Baki Harish?
Yes, sir.
Okay, so this is a AMS journal of Applied Meteorology and Climatology. So a lot of questions, and they asked a lot of questions, and We had to revise it many times, 2 times. 2 times.
Yes, sir. 2 times.
We had to revise it 2 times. Okay. So they were asking, how did you get the parameter? How did they get that? How did we get that parameter? Is in the other paper. The other paper is not getting accepted for a long time. So it was, but we have put it in the archive. They said it is in the archive and all that. It's good. Now both the papers are accepted, and we are able to give a suite of algorithms for both sensitivity study and calibration. So you can take a look at this. It is available online, right?
Sir, it is just a preprint, sir. Like early access they released. Once the proofs were completed.
No, but we have not corrected the proofs.
No, sir, they have not provided us.
They have not proofs. It's still in proof stage. Okay, all right. Yes. Okay. Okay. Now parameter calibration. This is the flow chart. 8 parameters already we have said, and selection of parameters. The choice of objective. What is the objective function you want? You have to generate sample. Then you do WRF simulation. Then you have to again construct surrogate models. Okay. So then using the surrogate models, you do the optimization. If the solution is converged, if it is yes, if it is not, you just go through the cycle. But now, without the flowchart, I'll try to make it little more clear. Okay. Suppose you want to play with the parameters. Okay. Let us say you want to play with the surface layer. 1 is the default. 0.5 to 2. How many values you will take? 0.5, 0.55, 0.65, 0.7, 0.8, 0.9. Okay, let's say 20 values. P4, 0.35, 0.36, 0.37. Then microphysics, Stokes parameter, scaling factor, ice fall, 8,000, 9,000. So it is endless. So there, obviously there should be a method in the madness. So what we do is, here machine learning, here all your numerical skills come to your advantage. So using a very sophisticated way of generating unbiased samples, which will explore, which will cover the whole of the parameter space. You be very frugal. You do only 100 simulations of the full model simulations, because each has to come out of a supercomputer. Each is expensive. Each, if you have to pay money, right? From this, what you do is you build a surrogate. That surrogate, you keep changing 0.35, pointing anything, right? So the surrogate is like a regression. Then you keep playing with the thousands and thousands of pseudo samples you generate, and then put it into that surrogate model. It will return the value of the output. What is the value of the output? We have chosen the value of the output as the root mean square between the observation and the root mean square of the observation and the simulation. Okay, that is the, so in machine learning it is called as a target. So that is the target. Now the target, what could you be? What could be your target? There are 8 variables. So if you want to do for each of these, it's a very tough exercise. So we decided that we will choose only 2 targets. What are these 2 targets? I'll tell you in a minute. Okay. And then if a set of parameters, the calibration turns out to be excellent for rain, it is not good for wind speed, then you have to arrive at a compromise. So this is a multi-objective optimization, because the tuned set of parameters for one output variable may give inferior results with respect to the other. Therefore, you have to go into the domain of optimization. How do we handle a truly multi-objective optimization problem? So there is machine learning, there is atmospheric science, there is numerical weather prediction. Finally, you have to come to multi-objective optimization. Okay. Okay. So now we set the goal as, what is the time now? 5:10. The objective is to minimize model simulation errors of 2 critical quantities. 10-meter wind speed, because the 10-meter wind speed gives an idea of the intensity of the cyclone, and the precipitation simultaneously. Precipitation, rain is a fundamental interest to us. So the RMSE obtained is normalized with respect to that of the default parameter values to make the objective. So we put normalized RMSE, NRMSE, to lie between 0 and 1. Okay. So to calibrate the model, first it is needed to obtain, just I told you 5 minutes back, you need to have sample. So total of 100 initial samples are generated using the quasi-Monte Carlo. Correspondingly, 10 tropical cyclones are simulated using the WRF model. So the initial samples 100 by 8 and the corresponding simulation errors for the 2 quantities, 10-meter wind speed and precipitation, are used for the surrogate model construction. Okay. Through the previous study, the GPR model is used for the surrogate model because we found out that it is the best. So 2 GPR surrogate models corresponding to 2 fellows. One is wind speed, one is rainfall. They are built using 100 samples. Then once you have a surrogate model, then sky is the limit. Then whenever your optimization program wants the output of RMSE for a set of parameters, you don't have to go to the WRF. you have to go to the GPR. The GPR model will be a surrogate or a replacement. It will be it's called a fast model. So it's a fast or a swift model or a quick model. That model will give you the your NRMSE. Okay. The solution now, what we do is, so this is basically now this is some another numerical trick which Baki, Harish and Sandeep have done. So it is an adaptive genetic algorithm. It trains, calculates the error, and then the new set, it is again put into the part of the training. It is an adaptive this thing. So this cycle keeps on going till the error reduces. Okay. So the solution obtained from GA is used as a new parameter sample, and again WRF simulations are conducted with it. The new parameter sample and corresponding WRF simulations are added to the existing data set. Using this, again the surrogate models. So what you do is you start with 100 simulations, then it again become 101, 102. So you keep going back and forth till you achieve this right side. Look at the northeast corner. So you still the normalized error does not change. Okay. So Baki, so from 100 you have to go to another 40, right?
Yes, sir. Another 31 for wind speed and another 41 for precipitation.
So you have to generate on. So I hope you understood this. What we have after the output of the GA, what we do is that new set of calibrated parameters, we again run the forward model, the WRF model, and that data is again input. And what is the final goal? Basically, the error should keep on reducing. Once you keep on doing it, the program will get sick of it and the error will not change. That's where you stop. Okay. Now look at the last line of this slide. It is observed that the 10-meter wind speed model converged at 131st iteration, whereas precipitation converged at 141st iteration. Okay. Now the NRMSE values obtained at the end are given here. Okay. WS10 0.7944. For precipitation is 1.18. For so you can see that 0.7944 and 0.887, which is given in blue. Okay. These are what are obtained from the optimization runs. Now, so far we optimized individual surrogate models. That means we got a set of tuned parameters separately for the 10-meter wind speed and the rainfall. Okay. But our goal is to simultaneously, there should be only one set of calibrated parameters. Now the problem is you can't say there is a one set of calibrated which will be super duper, which will give the best performance for all your variables. That is not possible. That is a greedy solution, which is not possible because so many things are going on, so many parameterizations are there. At least, I mean, coming to this stage itself is a big. So we have crossed 7 seas to come to this level. So therefore, we have to change our strategy. So we have to look for a compromise solution. They say no alliance, common minimum program for alliance of parties which are ideologically opposed. Okay. So like this is they may not be ideologically opposed here. They may be ideologically non-aligned. Okay. In that case, okay, 10-meter wind speed is giving one set of parameters. Precipitation is giving one set of parameters. What do we do? So we go to multi-objective optimization. Okay. So please look at this. So whatever is giving the best precipitation, look at that view graph on the right side. If you want the best this thing for precipitation, it is not the best for. It is not the best for. These are all the NRMSE, right? Baki, figure 10.
Yes, sir. Yes, sir. NRMSE values of.
You want minimum in both. Okay. So the greedy solution will be the origin itself, correct?
Yes, sir. Yes, yes. Sir.
The greedy solution will be the origin, but you will never get it. So this is what they say, life is a zero-sum game. It is very clear. It is a zero-sum game. So you take your pick. You want to focus only on precipitation, use a set of scheme. You want to focus only on the intensity, you can focus on some others. Now, if you give a weightage of 0.5, then we broke the impasse. Okay, we have broken the impasse, and then we will say that. So this way of finding out a compromise solution is there's a technique called TOPSIS. Okay, technique of preference. Okay, technique of preference with similarity to the ideal solution. Okay, so it is like this. So your objective 1, so your objective 2. So this is called the Pareto front. named after the Italian mathematician and economist Pareto, who said that 80% of the work in any company is done by 20% of the people. Okay. Now, this is a greedy solution. So this is negative ideal solution. So my final solution should be, so this should be min and this should be max. Okay. Now you choose a point here, here and this. So we try to do that. That is called Topsis algorithm. So Topsis is also, code is available somewhere, no? Baki?
Yes, sir. Code is available in Python, sir.
Topsis code is also available in Python. Topsis is something you'll have to learn if you're looking at multiple objectives. Okay. Okay. Now, if you see multi-objective, what you can see is the best wind as far as wind speed is concerned. So 0.79 has increased to 0.82. Okay. But what happens is you will not get the best for each of these individual, but you will get a compromise. That means for what is that solution will be. So if you put it in, so you'll say the least worse off. You're the least worse off in an overall sense. Okay, the least worse off. This is a, for example, if you look at the field of game theory and all that, they do a lot of these things. Okay, I want to minimize the maximum loss, maximize the minimum profit, and all that. There's something called the two prisoners dilemma. You just look at that problem, prisoners dilemma. Two people are caught and so for some theft, and if both of them speak the truth, they will have some advantage. If they, and then the police officer goes and interrogates them, and what kind of response they will give. So this results in what is called the Nash equilibrium. Okay, so that is a fun. So game theory. So I have been trying for a long time with my students to use game theory in optimization, and batches after batch and batch after batch, the BTech students miserably fail. So I've still not got a handle how to use. It's a powerful technique, particularly in multi-objective framework, how to use game theory in optimization. So this is one, this is an open problem, right? So for engineers, all right. Okay. Now, fine. So now this is one framework. So like that for your, whether it's you're in glaciology, you're studying atmospheric, what is that, aerosol, optical depth, and this thing, whatever. So whatever be your field. So if numerical solutions are very expensive, you can go with a limited set of numerical solutions, use machine learning to develop a surrogate. Then study the sensitivity using some scientific methods. And then if these numerical simulations use a lot of parameters and the parameters have to be calibrated for you to get better forecast, look at some benchmark or a truth. Okay. So run repeated simulations, do a surrogate, then use some optimization technique, try to arrive at the best set of parameters. Now what you do is, now you run your case, the best set of parameters for some other case which the model has not seen, all this jazz the model has not seen, see whether it performs well. Okay, so this is one way of proceeding further. All right, now I will just quickly look at a reading from another paper published on ISMR Info. Professor JS gave me this paper. All right, so please remember, in last class we tried to use just the brute force time series in the past Indian summer monsoon rainfall and try to predict the future rainfall, and it was not giving the desired result. The R squared of training itself was very less. Now there's something called teleconnection which people use. Okay, so this is a popular term. That means instead of using a single time series, make other people your compatriot or your companion in the crime, as they say, right? He is my co-worker in the crime. Like that, you try to see some other variable, some other surrogate, some teleconnection, okay, and put all, and if these are available as a time series and you put this into your neural network, put a masala and try to see whether you're able to get a better handle. Okay, so Needless to say, ISMR is very important for agriculture and Indian economy and forecasting. The ISMR is like a key problem, right? And there is a non-linearity in the data, and there doesn't seem to be a set pattern, and it is very defiant. It is very defiant, and it cannot be tamed. This problem, it's not easy to solve this problem. Okay. Now, if you look at what are the climate indices which affect this ISMR, so this is a paper by Adarsh and Changa Reddy. I think Baki is in touch with the authors to find out more details. So if we get more details, I'll keep you posted in email. So the quasi-biennial oscillation, El Nino oscillation, sunspot number, Atlantic multi-decadal oscillation, equatorial Indian Ocean oscillation. So if these are the climate indices, so what you do is they propose that there is a cross correlation of climate indices inputs to a machine learning algorithm. You put it as a input to a machine learning algorithm, it can provide better forecasting. So they adopted what is called empirical mode decomposition. This is some technique for multi-scale decomposition of the time series, not time series. So this is typo rainfall data set, and they use some transform to estimate the cross correlation. Finally, this EMD, empirical model decomposition, and linear regression were used for precipitation forecast. Okay, this is you can go into this paper and get the details. So basically what they've done is to predict the rainfall during the June. Okay, this model was used. The past 5 years of rainfall of June. Okay, rainfall in June, T-1, T-2, T-3, T-4, T-5, and then corresponding to this, they found out what is the highest correlation of the climate indices, and using the 5 years rain, past 5 years rain for June and the climate indices, they will get the rain for this June. Like that, you get the rainfall for July. Then you get the rainfall for August. You get the rainfall for September. You add all these four, and you get the rainfall for the monsoon. This is another attempt. Okay. So what is the training set? 50 to 88 is used for training, whereas at 1989 to 2012 is used for validation. Okay. So they got a good correlation. Training was 0.972, but again, that testing is only 0.798. So which means it may work for a few years, and we don't know. We are never very sure. Okay. There exists still scope for further improvement in model accuracy. Baki and I, we are also trying. We are taking 11 months of input, and then the 12th month it will return, and then learning and forgetting. So that also a possibility. Then we can also take a cue from this, and using that LSTM, which I explained now, we can also use some climate indices and improve. So we will see how far we succeed. Okay. So some advanced topics which are there in neural networks, basically RNN, recurrent neural network. They're useful in handwriting and speech recognition. Okay, so considerable math and algebra, everything is involved. The convolutional neural network is basically again some intermediate layers, or instead of deep learn, instead of intermediate hidden layers with neurons like this, there are some processing layers. It is mostly used in image processing. There are too many details, and they want to process the image. The LSTM is long short-term memory, is making predictions from time series. So where there's a concept of forgetting. So you learn and then you forget one data, then you do so learning and forgetting. So that is LSTM. Reinforcement learning is a big thing now. It's a big thing. So where it learns from mistakes. When it learns from mistakes, with the machine learning, the AI is moving slowly towards strong AI. Okay, where they feel that you can understand human behavior. So it predicts and it finds out there is a mistake, and then it learns, and then it changes. So basically, it's like robotics and all that. So reinforcement learning is used in many fields now. Deep learning, when huge data is available, you have multiple deep layers and so many weights. Okay, which it won't cause overfitting because a lot of data is available. You can do deep learning. The Bayesian neural network is a very fancy. Is a very good. Suppose there is a weight W. You say that the weight W is also like this. Huh? So all the weights have a distribution. Huh? So you build in a probabilistic approach to a neural network. So this is big time now. So it is not ANN now. A lot of people BNN. Huh? Bayesian neural network. Okay. So this is also a current thing. Now I will just give you a 5-minute thing on. Now we have done too serious stuff in today's class. let's have some fun and let's do some how ML is applied in some other field. Okay. Okay. So 101. Okay. So let's say how we can use ML for online fraud detection. Let's say X. Okay. So some Sharma ji. Let's say some Sharma ji is there. And so he is account and Amazon. Okay. Now if you consider just one attribute. Okay. So price. Uh, 200 rupees, 1000 rupees, 2000 rupees, 4000 rupees, 6000, 8000, 12,000. This is the price. Let us say last 2 years he is buying like this. So this is some histogram. Now you can plot a. So now if you look at this price. So the Amazon probably has something like this is Sharma ji. Now tonight 10 o'clock Sharma ji is logging into Amazon. Okay. Now, so his mean is, let's say he is always buying things, his average is around 4,000, 5,000. Now suddenly a 84-inch Samsung TV or something which is like, let's say the price is here 1 lakh. Now what it will do is, now it has put a Gaussian for his behavior. Now it will generate a probability of P equal to 0.01, say. If P is equal to 0.01, so a red flag will be generated. So I am oversimplifying the thing. So probably a red flag will be generated, say that somebody else has stolen his. Okay. Now for the same thing, suppose he is 5,000, he is buying a plastic bottle, some Milton or some Tupperware or some bottle for 100 rupees. That will also generate a probability of 0.01, correct? But that 0.01 they don't suspect because it is, you know, even if it goes, it's okay. But the same probability of 0.01 when it comes on the right side of the spectrum, it is a red flag. Okay. So this is this is how machine learning. So constantly somebody is looking at a behavior. Now I oversimplified the problem. Now apart from this, what it can do is, okay, what it can do is 1, price, 2, location, time. Okay. It can take all of these attributes and then go to a logistic model. Okay. It can go to a logistic model and you can sum, just like our rainfall classification problem. From this it goes to a sigmoid and then the sigmoid generates a y bar, y plus. Then you will, then it will have a online, it will say fraud or no fraud. So finally it is a classification problem. So if it's a fraud, if it thinks it's a fraud, then it will not allow the transaction to go through. So you can see that there is no forward model, there is no physics, there is no tuning of parameters, whatever. So in all this, so it is rapidly, it's rapidly expanding in many of these fields. What do you think many of the IIT BTech students are doing after their job mostly is finance? Basically, they'll be looking at all this. Okay, so they will probably build up some models. So you can see that here also there is no neural network. Okay, here also there is no neural network. It's a basically a decision tree, right? So here, at least we can say this is explainable machine learning, because suppose the customer says, why didn't my transaction go through or something, or it goes to consumer court or something. First, this the analyst must be able to explain to his bosses what is a model and this thing based on past data, this thing, whatever. Therefore, at least this you can explain. But if you go to the neural network, there may be a problem that it appears to be mumbo jumbo, though I believe that mathematically everything can be worked out. All right. Thank you for your attention. So I'll be here till the end of June. So you can drop by in my office, these 303, or you can send mail to me. All right. So any questions on today's? Anybody has any questions?
Balaji,
Sir.
I want to ask you, in the WRF model was cyclone prediction, what was the accuracy you achieved after all this? Rainfall accuracy of cyclone.
Rainfall accuracy, baki 10% reduction we got, right, in RMSE?
Yes, sir. For rainfall, we got 10% reduction. For wind speed, we got 17%, sir.
So 17% in the wind speed and 10% in the rain, sir. Error compared to default. So our our baseline is the default value. Compared to default, how much we improve?
But is it worthwhile? 10% reduction after all the effort?
But it's okay, sir. So now computer. So 17 is still it's not within the error band. No, it's outside the error band. It is. I think it is going in the right direction.
No, but you have to also put in the cost of computing. So what? Suppose somebody wants an advice. Is it worth using in real time this kind of thing?
Yeah, no. But so what? So
no,
the answer to the question is
no. Sorry. Let me clarify, Balaji. I want to ask your best solution you got through all this. How much it differed in the parameter values from the default value? How much it differed?
So some parameters were really we have shown in the paper, correct?
Okay.
So some parameters were way off.
Okay.
So what I'm saying is some group should work on this, and then they say they can give guidance to other people. So please check out. I'm not saying that everybody who uses WRF has to do this, but there should be a modeling group which should do this.
Okay. Thank you. I'll read the paper and get back to you.
Yes, sir. Sure, sir. Anybody else? Pradeep, Tashwin, Nidya?
Sir, even after this calibration, once we combined it with the assimilation, the improvement in track prediction is improved up to 45%, and like wind speed, like maximum sustained wind speed improved is also 35%. Like the calibration has further advantages if we combine it with some
assimilation,
that kind of data strategies. Yes.
Yeah, so we have actually done assimilation also, which I did not present in today's lecture. So I will probably do it in CDS next week.
Okay.
Okay. Anybody else? Okay, then. Thank you. So we'll call it a day. So thanks for your attention. So I'll end.